so we have just considered our source, the energy momentum tensor, to be something we will expand in terms of some Fourier terms. We want to consider in this case a single Fourier component. Our goal in this is to show that we can write the energy momentum tensor in terms of only the space components. This is one thing that we use, of course, in the last expression, in the last presentation. We had summation over omega in this case. Now, like we said, we're considering a single Fourier component. So we could write it in this form, or raise the first index. Of course, it could be some row which we can again change back to mu, and that is what we get. And our conservation law, of course, if we recall, was that this, when we take the divergence, the four divergence of this, we get 0. Of course, we could sum this left-hand side over mu, and the first time will be for 0, 0, then plus tii, of course, for which we mean that I ranges from 1, 2, and 3. And so we could sum that or take that to be down anyway. So looking at these two expressions, these two terms, this plus that being equal to 0, or we might as well write them as that. This is what we get when we try to make one subject of the formula. Now, looking at one part of this is that this, for instance, is equal to that. We just replace the mu and mu over here with the I. Okay, just maybe the I have been replaced in this expression, especially for this one here. We just replace the I with the mu there with I. And so we have I all over the place where we usually have, where we had the mu. Of course, we can do the same for the not, such that we replace mu every year with not. And of course, so it's just to show that we have here the Fourier expansions in these components. And at this moment in time, we want to see how to calculate this by, of course, if you recall, ti nu comma I simply means the ti nu, the x I, we're just differentiating that with respect to the space component. And so at this moment in time, it means that if this does have this, okay, maybe I should say if this does have this Fourier expansion, differentiating that with respect to the space component, that's xi, it means the entire term. So the differentiation, even though this alone is the only one dependent on x, this is not dependent on x, it's just a time component. It means differentiating the entire term. So we just want to say that we are really differentiating the whole term with respect to xi. Of course, as we have said, this is independent of time, and because of that, it's okay if we just write it as that. And at this point, we're just going to add plus cc for complex conjugate to avoid proliferation of terms. But in the end, of course, we are just going to make every interpretation or make use of just the real part and not the complex part. And so because of that, I will be using cc all over the place. The same, of course, is applicable when we differentiate with respect to time. It means, again, when we are acting on this, differentiating this expansion, which has been written in terms of this single Fourier component, if we were to differentiate the whole term there with respect to time, what it means in essence is actually we're differentiating this first term entirely with respect to time. And on doing that, of course, this is independent of time. And the only thing we differentiate with respect to time here is this. And so that brings us down a minus I omega, and leaving this just the way it is, and everything else is just the same. We have no term or residual as a comma 0 anymore, like we have comma I here. And so, taking note of the fact that the Fourier expansion, that is, or we can take an inverse Fourier transform if you like, that is how you may see this as, that's t mu nu of k comma omega could be written in this form. Or again, if you invert it, if you write for t, the expansion for t mu nu, but then of x omega, this is in k omega, this is x omega. The only thing then is that we have the x prime, and x prime here being replaced by k prime, and k prime too. So, or again, at this point, we can decide to raise the first index, and then again, we may have this to be written in this form. Of course, we are doing this because this is the form in which it will be suitable for us to be able to make use of the transformation laws that we have derived. Now, at this point, then again, we can use, just like we've made mention of the Fourier expansion, this Fourier transform here, we can make use of this, writing this ti nu of x comma omega. If you recall, we have here a differentiation of ti nu of x comma omega. So, what it means is that if this is what it is, we really will have to differentiate. So when we differentiate this with respect to xi, we will actually be differentiating the entire Fourier transform with respect to xi, and this is what we have done here. Now you can see that when we do that, this k dot x might as well be written as k sub j xj. So of course, none of this here is dependent on x, as you can see. This is just k prime comma omega. So if I were to differentiate this exponential function with respect to exponential factor with respect to xi, I will get a Kronecker delta of ij. And then again, of course, that will bring me down a k sub j. But then evaluating the Kronecker delta changes the j to I. So you may want to be careful to recall that this is a complex number I, but that is just some index. We might as well use j's again or iota or anything else just to avoid the confusion. But having said that, I hope that is cleared up. At this moment again, I have an I here, and then in the bracket again, so all I've done is just to have, of course, I reverted back to the convention of just having k prime dot x. I left the ki inside. So what it means in essence is this expression here that I've found, this expression here is what I've called q here. And if you take note of this, this was q here. And this, of course, was the differentiation with respect to xi, for which this here is x comma t. What we have found is the differentiation of the ti nu, but s comma omega, not s comma t. And so I will simply substitute this expression, which I have obtained here, as you can see. So what I've done is simply to have substituted this expression. Sorry for all this. So I bring it back in and put it here, and which is why you can see now the factor of e raised to power minus I omega following me and plus cc. Now again, I come back here and then I say, okay, fine. Looking at this expression again, which I've called P here, and of course P is what I've named this. So all I'm doing now is simply just to write out the Fourier transform for this, and this is what it is. There is nothing to be done other than just put it back into this expression, so that I still have minus I omega, but then maybe I will have to take the omega inside. The omega will multiply this. So if the omega multiplies this, and recall that I have a minus I, so if I were to use this conservation law that we had before, the minus here, first of all, will cancel the minus here, and then the I here will cancel the I here on the left-hand side. I'm left with just omega, which I can take back inside the Fourier transform that I had here initially. So in other words, what I've done is to have equated just to do what I was supposed to do, the derivative of this ti nu comma I, and then equal to minus t naught comma naught. Of course, this t naught nu of s comma t differentiated with respect to time, we have already done here. If you recall, we already done that, and this we finally have written as that. So at this point in time, of course, everything else is easy. Take this to the other side of the integral, and the whole thing becomes equal to 0 for any arbitrary factor of this exponential factor, which will imply that what I have in the bracket then is equal to 0. And if you look carefully, you can see, of course, this is sort of the dot product. This is the time component here. So it's just like saying you are taking the dot product of k mu and then the energy momentum tensor, the mixed energy momentum tensor, as you can see in this form. So this expression in essence could be written as k mu t mu nu all equal to 0. Or, of course, we can just make this part of it subject of the formula, lowering I and then 0 in that form. And this is what we get. We can do that with impunity, and this is what we have. Yeah, at this point in time, then what it means is here, for instance, okay, well, there's nothing much other than the fact that if I were to choose nu, for instance, in this expression, if I were to choose nu to be j, then I will have here what I will have. Okay, maybe I decided to invert it the other way, so I started with the right hand side. This is omega multiplying t sub 0 j. This will be equal to k sub I t sub I j, because the nu then has been replaced with j. Then I make this subject of the formula. Okay, so this was what I made subject of the formula here. This expression is simply saying that this is symmetric. So t sub 0 j is simply equal to k sub I divided by omega, and this is what I get here. Now again, I can choose nu to be equal to 0. If I did that, then I'm going to have 0, 0 here.
This is 0, 0. And then I have here with me omega, of course, again. And then what I have here is ki. The nu here has been replaced with 0. Now, making t 0 or t naught naught subject of the formula, what I'll get is k sub I all over omega. K sub I all over omega. And then, of course, as you can see over there, k sub I all over omega, t sub 0 I. But this expression, we could also rewrite from this one here. As you can see, what we obtained here actually was t sub 0j. But I might as well have written that expression for t sub 0i. And as a matter of fact, what I can try to do is just interchange between I and j all over the expression. Then it means that what I'll have here will be k sub j. Then this will be t sub ji. And of course, this is symmetric, so I can write it as t sub ij. So if I were to substitute this expression for t sub 0i here, then I will get k sub I, k sub j over omega squared. Now, omega is the magnitude of the wave vector. So dividing that by the vector itself, which is written by k sub I, gives us a unit vector for both of them. What it means in essence is I could have as well written this expression as t sub 0j equal to k sub I hat t sub ij. And that is just out. And with these expressions, you can see we have written for every such t sub 0i in terms of a space component. As a matter of fact, you can say we can make this subject of the formula, and we have written that in terms of the space component. And the completely temporal part we have also written here in terms of the space components. So just like we said right from the beginning, we have written the energy momentum tensor completely in terms of its space components. Okay, so very quickly, just a final note, something I wouldn't walk out in detail anyway. We just want to make mention of the fact that with this conservation law, or this being equal to 0, we can show that this expression for the polarization tensor that we have just obtained in the previous presentation, that this finally obeys that. Of course, it's a very simple procedure. You just have to take note of the fact that when you substitute this on the left-hand side and on the right-hand side, well, one thing you will have to do is to raise the nu here, write it in the mixed form, just like we have been doing all along. Then contract mu and nu, specifically because of this term here. And recalling that k nu, for instance, in this form could be written in this form. All it means is, anyway, when you have the metric tensor, because when you are going to be raising the mu and nu, you are going to be writing this eta mu nu as eta mu nu. And so when you have that written in that form, of course, since we are using the Minkowski metric for raising and lowering indices, and this is what you may have. So I think I'll leave this as a very simple exercise for anyone who is interested with all these developments to show that both the left and right hand side of this expression, that's the left and right hand side of this expression, are both equal to this. And so it's just to say that with this being equal to 0, we can see that the polarization tensor obeys our condition, which we have always, if we recall, was something we obtained from the harmonic gauge. Thank you so much for being with me in this presentation. Let's see you again in the next one.